Alright, the problem attempting to solve is building a trebuchet that allows for the longest horizontal distance and the strongest impact speed. Students should design an optimal trebuchet using online resources and their knowledge. The trebuchet should also be designed to be accurate. In doing this, the trebuchet should hit the same target multiple times. Students will be tested by attempting to hit a toy castle. Groups will be graded on the distance away from the castle their projectile lands. Students should document their build and make calculations throughout the process. As our research, we came up with a trebuchet is a specific machine used to launch projectiles. Trebuchets were used in ancient warfare to launch rocks and other large objects to enemies. All trebuchets consist of a lever on an axis, a counterweight, a sling, and a projectile. There exist 3 different types of trebuchets: swinging counterweight, fixed counterweight, and floating arm. A swinging counterweight trebuchet does not have the counterweight attached to the lever arm. This allows the counterweight to fall more vertically because the lever doesn't dictate the fall. In a fixed counterweight trebuchet, the counterweight is attached to the end of the lever arm with a string. This means the trebuchet falls in a circular motion. This is the most simplistic design due to the fact that the counterweight basket, this is because the counterweight basket does not have to be made. The final type of trebuchet is a floating arm trebuchet. This is the most complicated design. It consists of a counterweight being placed in a drop channel. The lever arm is attached to a wheel, and when the counterweight is dropped, a wheel is spun, forcing the lever arm to launch the projectile. Following the research, it was decided a swinging counterweight trebuchet should be built due to its relatively simple design. A swinging counterweight design also allows the counterweight to fall more freely, which will produce more efficiency.
Here's 45 degrees versus 30 degrees. So that's 0.4 meters. This makes sense, I think.
Yeah, it makes sense. It's
Length of sling should be the same as
the length of the long.
Alright, so we bought some wood from AC Moore's. We got these, I don't know, 1/2 inch by 1/2 inch balsa wood blocks. Those are for the frame. This is 1/4 inch by 1/4 inch. This is for the lever and the arm. This is for the sling to rest on. This is leather that the sling's going to be made out of. This is to attach the counterbalance to the lever. This is our counterbalance. And this is wood glue. That's all we got.
Alright, so what we're doing now is we're finishing up our design drawings. So initially we did the sling. We're doing the counterbalance, which we finished. The arm length, which we have finished. And right now I'm working on the trebuchet's base, the side view, and then we're going to do the top view. That's our design specifically. The entire ratio is just 1 centimeter to 0.5 centimeters. And that's about it.
Yeah. Check on top of the black cabinet with the computer at 20%. It's 30 degrees outside.
Let's go the other way.
What is Alex doing exactly?
You missed a spot. Missed a lot of.
Alright, so next we're going to construct our base. So we're going to take a plank for our sling to rest on, our 2 sides, our 2 widths, and they're going to go together in a fashion that's similar to this. And then we're going to glue them all together and show you what it looks like when we're done. Alright, when you're done constructing it, it should look something like this. The platform and then your base. Alright, now we're building the supports for our actual lever and pivot. So what you're going to do is you're going to take one of these and one of these, and you're going to connect them together like that, and then you're going to put on one of these metal supports. And then afterwards you're going to glue them onto the base of your trebuchet so that eventually we can attach our pivot. All right, after you're done gluing everything together and it to your base, you should end up with something like this. And of course, you're gonna clean up all the glue that's on the sides and on the bottom, but it should be pretty straight. It should be at right angles, and you should be able to put your fulcrum in between the two. All right, next we're going to create our lever. Well, we're going to attach our lever, which we've already created. All right, so what you're gonna wanna do is you're gonna have a hole right there at 5.5 centimeters. You have a hole up there for your wire that's going to attach your counterweight. Now, actually, the only thing you really have to do to this lever is attach your finger, which is this little piece of wire or nail or whatever you want to use, and you're going to put it into a hole that's drilled in the perfect center at the top. So you're going to add a little bit of hot glue, or any glue, it doesn't really matter, at the top, and you're going to put in your finger. Like that. And that's going to help you to aim your projectile. All right. So you're going to take your piece of leather and you're going to cut it using an X-Acto knife to the shape that we've designed, and you're going to sew it together with needle and thread. All right. So this is our finished pouch. It's folded in half like this. That's how it will carry the ball, and this is it completely stretched out. And if we're being completely honest, although it looks like the simplest task in our project, this took Michael 2.5 hours to build, and he broke 5 sewing needles and sent one into his thumb. So, yeah, you're gonna have fun with this one.
Be careful. Please be careful.
All right, we're gonna take all our separate components for the lever, and we're gonna put them together. So the pouch, the counterweight, the wire that attaches the counterweight, and the lever itself. All right, so this is what it should look like roughly, with your sling attached to the end that has the finger, and then your counterweight attached to the end that had the hole. Next, we're just gonna put all our lead shot, which is what we're using as our counterweight, into our container, and then we're gonna build the whole trebuchet and show you what it looks like when it's done. All right, so we're finished assembling all the components of the lever, the counterweight, and its wire, so it can swing freely. The lever itself, the finger, and the sling, and now we're going to attach it to our base of the trebuchet. So we're going to use this axle, and we're going to slip it through the holes that we've created at the top. Again, all the dimensions are found at the end of the video. And we're going to put it through, and we're going to finish our trebuchet. That's what it should look like roughly when it's done. I mean, you can clean it up, paint it whatever color. We chose black because black's awesome, among other reasons. Yeah, we're done. Test it out, of course, we've got videos of that.
Bad big in LA. Oh! That hit it. No, it did not.
It hit it. It hit the
Nine? Yeah!
All right. So to calculate out our average range, what we did is we held 5 trials. Now, we measured them in feet and then converted them into meters, and these are the conversions. So for trial 1, we had 6.895 meters. For trial 2, it's 7.596. For trial 3, it was 7.403. For trial 4, it was 7.480. For trial 5, it was 7.506. Our average for all 5 trials was 7.376 meters, which is the average meters we used for our calculations. All right, so this is our calculation for efficiency of our trebuchet. So we initially listed all of the variables that you need: height of the mass, the counterweight, the height of the pivot, the launch height of sling, the total height at launch, the height of the counterweight, the mass of the sling, the mass of the projectile, the mass of the counterweight, the mass of the long arm, the mass of the short arm, and then we found velocity using our kinematic equations. So our kinematic equations that we utilized were change in y is equal to VIY times time plus 1/2 AT squared, where t is time. Then we used change in x is equal to VIX times time. Now we input our variables. We know that our change in y was the negative distance that we started from converted into meters. So negative 0.364633, and that's just equal to VI sine times 43.5 plus 1/2 negative 9.8 t squared. Then we figured out our equation for x. So 7.376 meters, which is what we found our average distance to be, is equal to VI cosine 43.5 degrees t. So then we discovered what t is, so we can cancel out our second unknown variable. So t is equal to 7.376 divided by VI cosine of 43.5. We input that into t's for our individual y equation. So you get negative 0.364363 equals VI sine of 43.5 times 7.376 over VI cosine 43.5. You can cross out the VI's because it's multiply and divide. And then plus negative 4.9, 7.376 over VI cosine 43.5 squared. And as you start to do calculations and figure out what each individual section's numbers means, eventually you get down to negative 0.364633 is equal to 6.99, which is just this calculated down, plus a negative 506.66, which is after you square each individual variable in here, an integer, and then multiply it by 4.9 over VI squared. And then you start to find VI. You subtract negative 6.999 over, and you get negative 7.3636. Then you switch VI squared and negative 7.363 because they are each on, one's on the divide and one's on the multiply, and to get this over here you have to multiply, and to get this over here you have to divide. So you get VI squared is equal to positive, because negative and negative, 506.661 over 7.3636. And you square root both sides and you get VI technically would equal plus or minus 8.295, but since time cannot be a negative, velocity went in the positive x direction, you get VI is equal to 8.295 meters per second. And then to calculate out the inefficiency, we do output energy, which is just the potential energy of our counterweight, divided by our input energy, output energy, which is the kinetic energy of the projectile, divided by the input energy, which is the potential energy of the counterweight, times 100. So that's just 1/2 mass of the projectile times its velocity, initial velocity squared, over the height of the counterweight times the mass of the counterweight plus the short arm's mass minus the long arm mass, the sling's mass, and the projectile's mass times gravity. So what that comes out to be is 1/2 times 10.25 times 8.295 squared over 0.112 times 1089.2525 times 9.8. Eventually you get 352.636 divided by 1195.5635 times 100, and your percent efficiency for our trebuchet was 29.49%.
Conclusion is the constructed machine performed as expected. Due to its small frame and relatively light counterweight, the horizontal distance was as expected. Energy was transferred decently between kinetic and potential energy. The efficiency we calculated was roughly 28%. When the counterweight was pulled up, it built up potential energy and it was stored. When the sling was released, the counterweight fell, which transferred potential energy to kinetic. This energy helped fling the lever arm with the sling and the projectile. The energy was transferred onto the marble, which forced it to go towards the target. Energy can never be created or destroyed, so energy must be stored in the counterweight and later transferred onto the projectile. The motion of the projectile is determined by the angle of launch and the initial velocity. Formulas can be used to determine the initial velocity with other variables. The other forces that determine the motion of a projectile is gravity and friction. Friction is constant, and friction occurs between the machine's moving parts in the interaction between air and the projectile while in motion. Due to the forces such as air resistance and friction, the efficiency of the trebuchet cannot be 100%. To find the percent efficiency calculations using kinematic equations as well as other formulas using energy output divided by the energy input times 100 was utilized. Among thus giving a general basis for possibilities of improvement.
Well, I'm gonna assume that you're never gonna have us use these again, and I'm just not gonna do it. So things are easier to throw away in pieces.